Dear students, now we are going to discuss our fifth unit. It is Fourier series. Fourier series, these are representations of general periodic functions in terms of simpler periodic functions, namely sine and cosine. So let us start. So first we define periodic function. A function f is called a periodic function if it is defined for all reals perhaps except at some points so perhaps except at some points means, for example, the function tan. Tan is not defined at some points as we know. So except at plus minus pi by 2 plus minus 3 pi by 2 etc. Tan is defined everywhere. So still we call it as periodic function. So this is first thing. And second thing is there, and if there is some real number p positive, some positive real number p such that f of x plus p is same as f of x for all real x. Okay. So this number p is called period of function f. Okay, for example, if we consider the function sine, then we know that sine of x plus 2 pi is same as sine x. Okay. Sine of x plus 4 pi is also same as sine of x. Okay. So these numbers are called periods. The smallest such positive number p is called as fundamental uh, fundamental period. Okay. So for sine function, we know that sine of x plus 2 pi is same as sine x, sine of x plus 4 pi is same as sine x, and so on. In general, sine of x plus 2k pi is same as sine x. Here k is 1, 2, 3, etc. Okay. So k is 1, 2, 3, etc. Not necessarily positive integers, you may take negative also. That means you can have negative values for k also. Anyways, so smallest such positive number p is called fundamental period. So for sine, smallest such positive means 2 pi. Okay, so 2 pi is fundamental period for sine. Okay. Fundamental period. Therefore, fundamental period of sine is 2 pi. Now we know the graph of periodic function repeats itself. Okay, so we have some observations, notes. So first thing, the graph of periodic function f in any interval of length p will have periodic repetitions. Okay, for example, if you consider sine function between defined on any interval of length 2 pi, then the other part of this curve will be simply a repetition of this part. Okay, for example, you may consider the curve between the values 0 and 2 pi. Okay, so the representation of sine in the interval 0 to 2 pi will repeat periodically. Second thing, okay, so what are familiar examples? Some familiar examples of periodic functions. Familiar examples of periodic functions are sine, cosine, tan, etc. Okay. Similarly, the familiar examples of non-periodic functions are exponential, e raised to x, then x, x square, x cube, etc. Okay, so all these are non-periodic. Next thing, if f is periodic function of period p, then f of x plus p is same as f of x for all x in R, real. Okay. Now consider f of x plus 2p. It is f of x plus p plus p. Okay, x plus 2p means x plus p plus p. Now this is f of something plus p, and by definition it should be same as f of that thing. So this should be f of this x plus p. Again we are using the same rule, so f of x plus p, it should be same as f of x. So what we have seen, f of x plus 2p is also f of x. Okay, and in general we can have f of x plus np is same as f of x. Okay, x in R, n is 1, 2, 3, and so on. Okay. Next thing, linear combination of periodic functions is also a periodic function. Of course, periodic functions of here we consider uh, periodic functions of same period. Okay. Linear combination. If f and g are periodic functions of period p, then so is f plus bg, means the function af plus bg, where a and b are constants, is also periodic function of period p. Now we discuss Fourier's representation of a general periodic function of period 2 pi in terms of sine and cosine. Okay, so topic is Fourier series of a periodic function. So first we consider functions of period 2 pi. Later on we consider functions of any period p. Okay. So first is simpler case, that is functions of period 2 pi. So we consider any function. Suppose that f of x is a given function of period 2 pi and is such that it can be represented by a series a0 plus a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x plus and so on. Next terms will be a3 cos 3x plus b3 sin 3x. Okay, and so on. So we can write this as a summation. Okay, so this is a0 plus summation an cos nx plus bn sin nx n equal to 1 to infinity. Okay, we can rearrange these terms because we are assuming that this series is convergent. Okay, so we are assuming that our function can be represented as a series. Okay, that means this series is convergent, and for each value of x, f of x is same as this right hand side. Then we write f of x equal to this right hand side a0 plus summation an cos nx plus bn sin nx n from 1 to infinity, and call the right hand side as the Fourier series of f of x, and call the right hand side as Fourier series of f of x. Okay, Fourier is name of mathematician. The coefficients ai's and bi's are called Fourier coefficients. The coefficients ai's and bi's are called Fourier coefficients of function f, and we have formulas for these coefficients. We are not going to prove these formulas, so our purpose is just to introduce this topic and we solve some examples. These are given by a0 equal to 1 upon 2 pi integral from minus pi to pi f of x dx. Okay. Second, an equal to 1 upon pi integral from minus pi to pi f of x into cos of nx dx. Here n is from 1, 2, 3 and so on. And bn equal to 1 upon pi integral from minus pi to pi f of x into sine nx dx. Again n is from 1, 2, 3 and so on. Okay, so these expressions are called Euler formulas. A0, an, bn, these expressions are called Euler formulas. Now let us solve some examples. Example 1. Find Fourier series of function f of x, which is defined as f of x equal to minus k is constant here, if minus pi less than x less than 0, the value of function is k if 0 less than x less than pi, and one more thing is given, f of x plus 2 pi equal to f of x in r, uh, and here k is constant. Okay, so note that f of x plus 2 pi equal to f of x means this function f is periodic function of period 2 pi. Okay, so here we can find Fourier series using these Euler formulas. Okay, one more thing should be noted that this function is not defined at minus pi, 0, pi, and of course it will not be defined for 2 pi, 3 pi, etc. Okay, so that doesn't matter because we have seen that this function should be defined on a real line, perhaps except at some points. Okay, so this is okay. Now let us find Fourier coefficients. Okay, solution. Let us find Fourier coefficients. So A0, first thing is A0, which is 1 upon 2 pi, as we have seen, integral from minus pi to pi f of x dx. Now we have seen that the function f has two different values on two sub-intervals, minus pi to 0 and 0 to pi. So we split this integral. So we write this as 1 upon 2 pi into, first we take integral from minus pi to 0, and in this interval f of x is minus k, constant. Okay, minus k dx plus integral from 0 to pi, here the value of function is k dx. Okay, so it is 1 upon 2 pi minus kx, limits are minus pi to 0, plus kx, limits are 0 to pi, and we get, so when we put the upper limit it is 0, when we put lower limit it is there is minus sign when we are putting lower limit. Okay, so we have three minus signs, 1, 2, and that minus sign, so this is minus k pi. Okay, here this is plus, upper limit gives k pi, lower limit gives 0, so this is 0, so a0 is 0. Okay, now we find an. The formula is an equal to 1 upon pi integral from minus pi to pi f of x cos nx dx. Again same thing, we split integral in two subintervals, so 1 upon pi from minus pi to 0, function is minus k cos nx dx plus from 0 to pi, function is k cos nx dx. So this is 1 upon pi. We may take k common, so we may write k upon pi. Here it is minus sign. Now integral of cos of nx, it is sin nx divided by n, limits minus pi 0 plus sin nx upon n, limits are 0 pi. Now we know that sin 0 is 0, sin n pi is 0, sin of minus n pi is 0. Okay, everything is 0. Okay, so we get a n to be 0, n equal to 1, 2, 3 and so on. Now we find bn. Bn is 1 upon pi integral minus pi to pi f of x sin nx dx, and this is 1 upon pi into integral from minus pi to 0 minus k sin nx dx plus integral from 0 to pi k sin nx dx, and this is k upon pi into minus integral of sin nx, it is minus cos nx by n, so this is plus cos nx by n, limits are minus pi to 0 minus cos nx by n, limits are 0 to pi. So this is k upon pi. This n in the denominator we take common, so n, and here we have the upper limit gives cos 0, cos 0 is 1, minus lower limit cos of minus n pi, it is cos of n pi, and cos of n pi is minus 1 raised to n. Okay, so cos 0 is 1, cos pi is minus 1, cos 2 pi is 1, cos 3 pi is minus 1, and so on. So in general it is minus 1 raised to n, minus the upper limit gives minus 1 raised to n, then minus, and this is again minus sign, so it should be plus cos 0, cos 0 is 1. Okay, so this okay, so we get 2 minus 2 times minus 1 raised to n, so we may write 2k divided by pi n into 1 minus minus 1 raised to n. Okay, so when n is even number, this will be 0. Okay, so when n is 2, 4, 6, 8, etc., this will be 0, and otherwise this will be 2. So the bn we get is 4k divided by pi n. Okay, now we are ready to write Fourier series because we have computed all the Fourier coefficients. Okay, therefore Fourier series of f is a0 plus summation a n cos nx plus bn sin nx n from 1 to infinity. Now we know that all the ai's are 0, a0, a1, a2, etc. So this is simply summation bn sine nx n from 1 to infinity. And just now we computed bn. So this is 2k upon pi n into 1 minus minus 1 raised to n into sine nx n from 1 to infinity. Okay, so this is required Fourier series. Okay. Let us solve another example. Find Fourier series of function f of x given by 0 when minus pi less than x less equal 0, and it is x when 0 less than x less than pi. Okay, and f is periodic function of period 2 pi. That means f of x plus 2 pi is f of x for all real numbers x. Okay. So let us find out Fourier coefficients. First we find Fourier coefficients. Okay, so a0 by definition it is 1 upon 2 pi integral from minus pi to pi f of x dx. Now the function has value 0 when we take x between minus pi to 0. So this is nothing but 1 upon 2 pi integral from minus pi to 0 plus integral from 0 to pi. So this is simply from 0 to pi, and in the interval 0 pi we have value x. So x dx. So this is 1 upon 2 pi into x square by 2. Limits are 0 to pi. So this is pi square upon 4 pi, or it is pi upon 4. Okay, so this is a0. Now we find an. An's are given by 1 upon pi integral from minus pi to pi f of x into cos nx dx. Now this is 1 upon pi integral from minus pi to 0. Function value is 0, so it is 0. So it is from 0 to pi, and in the interval 0 to pi the function value is x into cos nx dx. Okay, now we use integration by parts. So this is 1 upon pi into, so this integral, so x is first term, cos nx is second term. So first term into integral of second, it is sine nx divided by n. Limits are 0 pi minus integral derivative of first term, that is derivative of x is 1, integral of second is sine nx by n dx. So this is 1 upon pi. Now here, if we put upper limit, then sine n pi is 0. If we put lower limit, then x is 0, sine 0 is also 0. Okay, so this term is 0. Okay. Now minus integral sine. We know integration of sine is minus cos, so it is minus, so this minus becomes plus. So cos nx upon n, and this n which is already there, so n square, limits are 0, pi. So this is 1 upon, we take this outside, n square pi. Now upper limit gives cos n pi. As we have seen, cos n pi is minus 1 raised to n. Minus cos 0 is 1. Okay, so this is required thing. Now we find bn. Bn is 1 upon pi integral minus pi to pi f of x into sine nx dx. Again, the value of function is 0 in the interval minus pi to 0. So this is 1 upon pi integral from 0 to pi. In the interval 0 to pi, function value is x. So x sine nx dx. So we evaluate using the same strategy. That means we use integration by parts. So first term x, integral of sine is minus cos nx upon n, limits are 0, pi, minus integral derivative of first term, that is 1, derivative of x is 1, integral sine nx, it is minus cos nx by n dx. Now this is 1 upon pi. Here if we put upper limit, then cos n pi, it is minus 1 raised to n, and here it is pi. So minus pi into minus 1 raised to n divided by n. Lower limit gives 0. Okay, x equal to 0 gives 0. Here integral cos nx, it is sine nx upon n. So this sign gives n square. Okay, limits are 0 to pi. Now this is equal to 1 upon pi minus 1 raised to n upon n. Here if we put upper limit, sin n pi is 0, lower limit sin 0 is also 0. Okay, so simply this becomes minus into minus 1 raised to n, so minus 1 raised to n plus 1. This pi gets cancelled and there is n in the denominator. Okay, so we here n is 1, 2 and so on. Okay, so for bn, for an also n is 1, 2 and so on. We are having all the coefficients now. Okay, so therefore Fourier series of f is a0 plus summation an into cos nx plus bn sin nx n equal to 1 to infinity, and this is equal to a0, that is pi by 4 as we already have seen, plus summation an is minus 1 raised to n minus 1 divided by pi n square. This is an cos nx plus bn. Bn is minus 1 raised to n plus 1 divided by n into sin nx, n from 1 to infinity. Okay, so this is required Fourier series. There are some more examples given in the exercises of the book engineering mathematics by Kreisig. Okay, so it is given in our syllabus. Thank you.